record?
Yeah, it's recording, yeah.
Ah, okay.
Yeah.
So now we have to get the zoom right.
Yeah.
So it's really zoomed in. Okay, now you can see everything. And now if I put it here, that should be good enough. Now you can see the TV screen and the board. Does it need to be more? That's probably good enough.
Yep, yep.
Okay.
Okay, so that's okay, that's good.
Okay, now where's the class?
No.
It's Columbus Days.
And you wanna use that class,
We're
yeah?
not close though, are we?
No.
No, it's okay. Thank you.
Welcome.
But I usually set my alarm at 7:30 and I got a notification saying tomorrow is Columbus Day. Do you want to change your alarm? I said nope.
I think we're not closed today.
Yeah, I know, but the character said that.
Yeah, I think a lot of things are closed today, but not Texas Tech.
Is there an event coming or this is the event, Columbus Day? Because Friday they were putting lights everywhere around the
That's for
university.
Christmas. Be prepared.
So Christmas started way early. 2 months before, more than 2 months before.
When is Thanksgiving?
And
Third
November.
Thursday in November.
Thursday in November.
Is this going to be your first Thanksgiving?
And oh, I'm just asking. And Halloween,
October 30th.
End of October.
Yeah, last day of October.
October
31st.
31st.
Yep. The day before All Saints Day.
Yeah.
Which is on November 1st.
Is it October 30 or 31?
31.
31.
Hey.
Is it raining outside? No.
That's weird.
How does this work? Okay. Okay, so we better go ahead and get started. Okay, so last time we were talking about this example of CO oxidation on oxygen-covered platinum 111. And we're using ion imaging-based techniques to look at the kinetics of this reaction. And there's these two channels. There's this hyperthermal channel shown in red, which has a very fast decay. And then there's this thermal channel shown in blue, which has a bi-exponential decay. One of the components is very fast, and the other component is much slower. Okay, and so, yeah, in the literature, this speed distribution was observed before, and it was attributed to a particular transition state of CO2 on the surface, which has a certain probability of either accommodating to the surface to make a Maxwell-Boltzmann distribution, right, that's in thermal equilibrium with the surface, or being released directly to the gas phase to give rise to the hyperthermal CO2. Okay, and so that's where we left off last time, but this mechanism cannot be the case because we know that there are two different kinetics, basically. The thermal channel has a slow kinetics, the hyperthermal channel has a fast kinetics, and if there was only one type of CO and one transition state on the surface, you couldn't have two different decay rates, right? Okay, so how do we figure out what's going on? Well, this reaction is being done in a regime where we observe pseudo first order kinetics. That means the concentration of oxygen on the surface is constant. And so, based on what we learned during the first couple weeks of this class, what you would do is you would analyze this in terms of a pseudo first order rate constant. So if you assume that there's two different processes, so there's a K1 process by which you have loss of CO from the surface by any means, such as desorption, then we can call that rate K1. And then if there's a second order reaction rate, we'll call that K2, right? So the rate of disappearance of CO is going to be K1 times CO plus K2 times CO times O concentration. Okay, and so that gives you an effective rate constant, K1 plus K2 times O. And the signal, right, the flux of CO2, which is what we observe, that's going to decay with this effective rate constant, K effective. Okay, and you can get both the K1 and the K2 if you measure K effective as a function of oxygen coverage, right? Because it should have an intercept of K1 and a slope of K2, right? If you plot K effective versus oxygen coverage. And so you can change the oxygen coverage by varying the relative repetition rate of the O2 nozzle and the CO nozzle, right? So if the O2 nozzle is firing less frequently, you're going to have less oxygen coverage. And then you can measure the effective rate as a function of oxygen coverage. So shown here, it's just shown as a function of relative repetition ratio of the two nozzles, which should be proportional to the oxygen coverage. And from this plot, you can extract K1 and K2. Okay, so the K1 should be the intercept of this plot, right? The zero coverage extrapolation. And you can do that for both the thermal channel and the hyperthermal channel. And if you look at what is the effective K1 from the thermal channel, it's these points that are shown in blue here. And on this plot, I'm comparing these points to the measured rate of CO desorption from 111 terraces, that's shown in triangles, and from steps, that's shown in circles and in crosses. And so you can see that the measured K1 agrees perfectly with the desorption of CO from step sites, but not from the flat 111 terraces. And so this is evidence that the thermal channel involves CO oxidation at steps because the competitive non-reactive channel, right, the K1 channel that gets rid of the CO from the surface, looks like it's desorption from steps. Okay? And even though on this 111 surface there's fewer than 1% steps, this is the dominant channel, this thermal channel. So that shows you how important, defect sites are in reactions at surfaces. And you can do the same thing with the hyperthermal channel, where here the K1 for the hyperthermal channel is plotted in triangles, and you can compare that to, again, the desorption rate of CO from steps and from terraces, and it's even faster than the desorption from terraces. So at high temperatures, it looks like maybe it's competing with desorption from terraces. At lower temperatures, it looks like some sort of diffusion rate. It's very fast. And so this leads us to believe that the hyperthermal channel involves CO oxidation at terraces, and the competitive non-reactive channel, right, the K1, is then diffusion from terraces to steps. Right, so that's how you lose CO from the terraces, is it diffuses to the steps, and then it gets more tightly bound to the steps. Okay, so that's sort of what we think from the kinetic data, but how can we be sure that this is really the right assignment? Well, we can do another experiment. That is, we can repeat the experiment at a single crystal surface that is cut at a different angle so that it exposes a large number of step sites. So this one is called the 332 surface, and every sixth row there's a step. And so if you look at the speed distribution on the atomically flat platinum 111 surface, which has a step density of less than 1%, you see this thermal channel and this hyperthermal channel. On the 332 surface, which has a large step density, the hyperthermal channel almost completely disappears under the same conditions. And so this confirms the assignment that this thermal channel is due to the steps, the hyperthermal channel is associated with the terraces. Okay, so there's this mechanism then. So CO lands on a terrace site most likely. It can either react with oxygen on a terrace site to make hyperthermal CO2, or it can diffuse to a step site, or it can desorb. Okay? If it's on a step site, it can react with oxygen on a step site. This is not the actual transition state structure, this is just a cartoon. But it can react with oxygen on a step site to make thermal CO2. But then there has to be one more reaction giving thermal CO2, because the thermal channel has this bi-exponential decay, where one has this fast decay rate that we associate with the decay rate of CO from terraces, and then a slower rate that we associate with the decay of CO from steps. So there must also be some way to get rid of CO on terraces via this thermal CO2 channel, so we assign that to some sort of terrace step reaction. Okay, and using this model, you can fit all the data over a wide range of coverages and temperatures. And the model fits both the 332 data and the 111 data, and the results are shown here. And so the desorption rates were fixed to the known literature values that had been measured previously, but then the rates of each of these reactions was fitted to the measured data. And the rates on the 111 surface are shown on top, and the rates at the 332 surface are shown in parentheses for each of these parameters. And you can see that the activation energies and Arrhenius prefactors on these two different surfaces, to within experimental error, they match one another almost exactly. And so previously, right, from these molecular beam relaxation spectrometry experiments, I told you that they had measured different activation energies as a function of oxygen coverage, right? That it looked like the activation energy was decreasing as you increase the oxygen coverage. But if you understand the mechanism better, right, that it's not just a simple mechanism, it's actually a complicated mechanism involving different surface sites, then it looks like the activation energy is much less sensitive to the oxygen coverage. Maybe there's a small dependence, but not very much. Okay, just a motivation. Why do we want to do this? Why do we want to go to these higher temperatures? If you look at the coverage on the x-axis and the temperature on the y-axis, most of the laboratory measurements of the kinetics of this reaction are done in this range shown here. But actual catalytic converters that convert CO to CO2 operate in this range here. And shown as a color scale is, based on our model, what is the fraction of the reaction that happens, that's hyperthermal, right? That happens on terraces. And so you can see that in the laboratory work, you're seeing almost entirely the reaction on steps, right, and defect sites, whereas in the real world, at these higher temperatures, you see almost entirely reaction at the terraces. And the reason is because desorption at very high temperatures becomes faster than diffusion to the step sites. And so therefore CO has to react where it lands because it doesn't have time to diffuse before it desorbs. Okay, so that is all that I wanted to say about that. Any questions? Okay, so that sort of concludes our examples about surface kinetics. And so now we're going to move on to the next topic, which is solution phase reactions. How do I turn this off? Here.
Oops.
Okay, that gives me most of the board. Okay, so we've spent a lot of this class sort of talking about reactions sort of with, gas phase processes in the back of our heads, because those are the simplest ones to understand, and that's where a lot of the most detailed experimental understanding of chemical kinetics has been developed, is in gas phase. But we've talked about surfaces, which can be quite complicated, but there are also a lot of reactions that are very important that take place in liquid solutions. And a lot of the times in liquid solutions, you can sort of ignore the solvent because it doesn't play a large role in the reaction, and you could just think about the reaction in terms of the reactants coming together and reacting. And so in cases where the solvent doesn't really play much of a role, often the rates that you observe in solution phase are quite similar to those that you would observe in the gas phase. And just as an example, if you consider the density of a gas at 1 atmosphere, that would correspond to the density of a solute in a solution at 4 times 10 to the minus 2 moles per liter. Right, so this would be a quite typical pressure to do our reaction at, right, 1 atmosphere, and 0.04 molar, this would be a quite typical concentration of solutes, right? And so you can see why often there's sort of a correspondence between the typical rates that you observe. But often there can be also quite important solvent effects. So let's say often reaction rates are similar. When comparing gas and solution phase. But you can have important effects of solvent. And the two that I would like to discuss in this course, one is cage effects. So that'll be today's topic. And the other time when the solvent often plays a very important role is when you have ionic reactions. So reactions involving ions often have large interactions between the ions and the solvents. And this can have a large effect on the reaction rate. Okay, so what is a cage effect? Well, let's say that you have solution with lots of molecules, lots of solvent molecules, and you have a couple of reactant molecules. Then it can actually be more difficult for the reactant molecules to find each other because they're surrounded by sort of a cage of solvent molecules and they're like boxed in, right? And the same is true, however, once they do meet each other, right? If you have two reactant molecules that meet each other, their interaction can be longer and it can have a higher likelihood of leading to reaction because the reaction pair can also be trapped in a solvent cage, right? And it has more time to explore different configurations and find the right transition state for the reaction. And so it's kind of like a good analogy would be, if you go on a date on the beach, then maybe your interactions are quite similar to if you go to like a dance hall, that's crowded, right? If you can ignore all the other people, right? But it might, if you're in a crowded dance hall, it might be more difficult to find your partner, right? Because there's people everywhere. But also, once you're dancing together, it might be more difficult to break apart, right? Because there's, you're crowded. Okay, so that's the basic concept behind cage effects. So solvent cages can make it more difficult for reactants to find one another. But it can also hold them together for longer. Okay? So, how do we describe motion of molecules through a solution? Well, one of the simplest models is Langevin's model for Brownian motion. So we can discuss this. This is a phenomenological model where Langevin assumed that the force on a particle in a solution is equal to a zeta parameter times the velocity minus zeta times the velocity plus some function f of t. And so this zeta parameter, acts as a friction parameter. So this negative sign here ensures that the force is in the opposite direction of the particle's velocity. So this term slows the particle down, right? This is due to friction with other particles. And then this f of t, this is a random force due to acceleration by other particles, right? So another particle bumps into you, causes you to accelerate. And this is just completely random. And so the assumption is, since these random forces are just due to thermal motions of particles, on average, the random force f of t is going to be 0 if you average it over a long enough time period. And so therefore, if you look at the average, the change in the average velocity as a function of time, that's going to be minus zeta times the average velocity. And then when you average this term, it goes to 0. And so this equation is trivial to integrate, right? We know the integral for this one. It's given by what form? Sorry?
Exponential?
Yeah, exponential decay. So v is just equal to the initial velocity times exponent of minus zeta over m times t. And so this basically just says that if you have a certain velocity, it's going to be dissipated. Right, so any directed velocity of the molecule gets turned into heat, basically. It excites the surrounding solvent molecules. Okay? So I'm not going to go through the entire derivation because we don't have time, but for t much, much greater than m over zeta, the Langevin model can be solved to give the average of x squared equals 2kt over zeta times time. Okay, so the mean square displacement, this is kind of a measurement of, on average, how far does a particle travel after a certain amount of time. That's going to increase with temperature, right? I think that's sort of intuitive. And then the higher the friction coefficient is, the less the molecule is going to travel. I think that's also intuitive. And if we compare this to the diffusion equation, remember the equation for diffusion was the mean square displacement is equal to 2 times the diffusion constant times time. And so therefore, with this correspondence, we could say that it looks like this Langevin model is describing diffusion with a diffusion constant of kt over zeta. Okay? And Stokes has shown that if you look at the friction coefficient for a spherical particle, then this zeta parameter can be written as 6 pi times eta, which is the viscosity coefficient, times the radius of the particle. Right, so this A here is the radius, and zeta is the viscosity parameter. Okay, and so overall, what we get from this model is that the diffusion coefficient in a solution, right, from the Langevin model would be kt over 6 pi times eta times A. And so therefore, if you have a solvent that's very viscous, right, that's sticky, leads to viscous flow, diffusion rates are going to be very low. If you have a low viscosity solvent, then diffusion rates are going to be very high. Okay, and so if you have very high diffusion rates, then you can think about the reaction almost like a gas phase reaction. It's going to be limited by the rate of collision, and then also by whether the colliding partners meet each other with enough energy and with the right relative orientation. However, if you have very low diffusion, right, high viscosity, then you can end up in another regime, which is called the diffusion-controlled regime, which basically says the rate of the reaction is limited by the rate of diffusion, because it takes a long time for the reaction partners to find each other, but once they do find each other, they have almost 100% chance of reacting. Okay, so let's look at that. Okay, so if particles take a long time to find one another, but react with high probability, when they do, this leads to diffusion-controlled reaction. Okay? So if we look at a very simple model for how does a diffusion-controlled reaction work, well, you can say you have reactants A and B. They have to encounter one another, and you can call the rate of encountering K encounter. But then, yeah, so they can encounter one another to form an AB reaction complex, but they could also escape the reaction complex at a certain rate, K escape, and then the reaction complex can react with a certain rate, K of reaction, to make a product. Okay? So this mechanism is almost identical to the Michaelis-Menten mechanism that we've discussed previously. It's just usually we're not in a regime where one reactant is much more highly concentrated than the other. We're not necessarily in that regime like we usually are with enzymes. But since we've already looked at this exact mechanism, I'm not going to derive the rate. You can look back in your notes at how we derive the rates for the Michaelis-Menten equation. And if you apply the steady state approximation, then you'll find that the rate of appearance of product is Kr times K encounter over K escape plus K reaction times the concentration of A times the concentration of B. Okay? So you can consider two limiting cases. Case one, let's say the rate of escape, right, from this complex to make A plus B. Let's say that that is much greater than the reaction rate. In that case, the effective rate constant is going to be, right, so K escape is going to dominate in the denominator, and we can ignore Kr in the denominator, and then we get K effective equals Kr times K encounter over K escape. And so in this case, it looks like basically AB is in equilibrium with A and B, and it just has a certain probability of reacting, right? And so this gives you the rate constant. But in case two, what if the rate of reaction is much, much larger than the rate of escape, right? This is what happens in the case where the AB is trapped in a solvent cage and it can't escape. Then you can ignore K escape in the denominator of this effective rate constant, and the effective rate constant goes to, so the Kr cancels, and you just get K effective equals K encounter. And this is where you have a diffusion-controlled reaction. Sorry, diffusion, Diffusion. Okay? Does that make sense? Okay, so our next goal is to get an idea of how to understand or how to estimate what you would expect a diffusion-controlled rate constant to be. And when you have a diffusion-controlled reaction, a simple model for that would be, let's say you have a particle A, And just for simplicity, we can assume A is not really moving, or we can consider just the frame in which A is located at the origin. And then there's a certain radius, R, capital R. And if another particle B, right, if the reaction particle B comes within a radius R of A, then it is going to react with A with 100% probability. And so we can say I'll draw B up here maybe. So the distance from A to B, I'll call that lowercase r. Right, so we're going to assume A reacts with B with, or I'll say every time B comes within distance R of A. Okay? And so over time, what's going to happen, so every time B encounters A, it's going to disappear. And so what that means is that over time, as the reaction reaches some kind of steady state, if diffusion is really slow, there's going to be a gradient of B around A. Right? So the B molecules that are really close to A, they're going to disappear, and there's going to be more B molecules further away from the A molecules, because the ones that are close react. Okay? So reaction will create a concentration gradient of B around A. Okay? And by definition, if you have a gradient and you have diffusion, right, then we know that there's a relationship between diffusion and gradients of concentration. So the flux of B is related to the gradient of concentration of B. And the relationship is the flux equals negative the diffusion constant times the gradient of B of R. So this equation basically just says if you have if you imagine some sort of planar surface, if you have a high concentration of B on one side of the surface, then the diffusion is going to go in the direction opposite the concentration gradient, so it's going to go towards lower concentration. And if you have a large concentration gradient, then you're going to have a large number of molecules per unit time, per unit area crossing the surface. Whereas, if you had a larger concentration of B over here, the diffusion would be the other way. Okay? And Fick's law says that, right, so this is the law for the
Mass.
diffusion as a function of time. So the change in B concentration at position R as a function of time, that's just the diffusion constant times the Laplacian, del squared of B. Right, we looked at this, we basically derived this when we were looking at these surface diffusion processes. And at steady state, the rate of change in the B concentration is going to be 0. Okay? So, what is this Laplacian operator? Well, del squared, you can write that in polar coordinates as the second derivative with respect to the r coordinate plus 2 over r times ddr plus 1 over r squared times d squared d theta squared plus 1 over r squared cotangent theta plus 1 over r squared sine squared theta. I hope I'm not making a mistake here. D squared e phi squared. Okay, but in this problem, the gradient of b around A is going to be spherically symmetric. And so it's going to have no angular dependence, right? So we can get rid of, oh, whoops, I left out a derivative here. This should be dd theta. Okay, so all of these angular derivatives are going to be 0. So this is 0, this is 0, this is 0. And if you have a spherically symmetric problem, you only need the first two terms in this expansion. Okay? So from this equation here, then if we substitute del squared equals these first two terms, then dB of r dt, well, that's just going to be the diffusion coefficient times the second derivative of b of r with respect to r plus 2 over r times dB of r dr. Okay? That's just substituting in the definition of del squared in spherical coordinates and assuming spherical symmetry. Okay, and so you can solve this. The solution has the form b of r equals some coefficient over 2r plus some other coefficient. Okay, and so you can prove this to yourself by substituting in this equation, this solution, and you can show that this has the correct form. And so what does this mean? Well, at large R, this first term is going to go to 0, and C2 is just going to be the bulk concentration of B. So C2, we could just call that the bulk B concentration. But the C1 coefficient, that's going to tell us something about the behavior of the concentration of B when you're close to an A molecule, right? How does the concentration fall off as a function of R? Okay, and so that's what we want to know is basically we want to know what is the concentration of B at distance big R. Okay, and so according to the model, dP dt, right? According to this basic model here, that's equal to Kr times the concentration of this reaction complex, which you can take that to be the concentration of A times the concentration of B at position R. Right? So this thing here, this gives the total concentration of AB. Okay? And so another way of writing this, so if you have B at R, then the rate of reaction, you could think of that as the flux of B crossing this dotted circle, which represents a sphere of radius R around A. Okay? And so you could say that it's the flux of reaction per unit area, and the area of the sphere is going to be 4 pi r squared times A. And so substituting from here, let's see, from here, right? This is just 4 pi r squared times the A concentration times the diffusion coefficient times the gradient of B, which in polar coordinates, if it's spherically symmetric, that's just dB of r dr. Okay. I think the next class is going to start in just a few minutes, so we'll finish this next time, and then we'll also talk about ionic reactions in solution. The other thing is, I need to send an email about the problem session. We can have a problem session this week. I forgot to do that over the weekend.
I found it.
Yeah, thank you.